NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math video where we'll prove an important inequality. Let's take a look at the problem we need to solve. Our problem asks us to prove the following inequality. The left side is open parenthesis 2 minus 1 over n close parenthesis raised to the power of n, which is greater than or equal to n, where n belongs to the set of natural numbers. To prove this inequality, we'll start by recalling an important formula. Let's remember the binomial theorem, which states that for any expression of the form a plus b raised to the power of n, we can expand it as follows: a to the power of n plus n times a to the power of n minus 1 times b plus n times n minus 1 over 2 times a to the power of n minus 2 times b squared, and so on until the final term of b to the power of n. Now, let's begin the proof. The first step is to rewrite the expression on the left side. We notice that 2 minus 1 over n can be rewritten as 1 plus 1 minus 1 over n. This gives us 1 plus open parenthesis 1 minus 1 over n close parenthesis. Next, we'll apply the binomial theorem to expand the expression. We'll set it equals 1 and b equals 1 minus 1 over n. This gives us 1 to the power of n plus n times 1 to the power of n minus 1 times the quantity 1 minus 1 over n, plus more terms that we'll look at shortly. Let's simplify the expression. Since 1 raised to any power is just 1, we can simplify the terms. The expression becomes 1 plus n times the quantity 1 minus 1 over n, plus other terms that are all positive. We're going to focus just on the first 2 terms of our expansion, since all other terms are positive and will only make the value larger. So we know that our expression is greater than or equal to 1 plus n times the quantity 1 minus 1 over n. Let's simplify the expression 1 minus 1 over n. This equals n minus 1 over or equal to 1 plus n times the quantity 1 minus 1 over n. Let's simplify the expression 1 minus 1 over n. This equals n minus 1 over n. So our expression becomes 1 plus n times n minus 1 over n. Next, we'll simplify n times the fraction n minus 1 over n. The n in the numerator and denominator cancel out, leaving us with n times n minus 1 over n, which simplifies to n minus 1. Finally, we add 1 and n minus 1. This gives us n. So we have proven that our original expression is greater than or equal to n. Therefore, we have proven the inequality that for any natural number n, the expression 2 minus 1 over n, all raised to the power of n, is greater than or equal to n. This completes our proof. We have proven that our original expression is greater than or equal to n. Therefore, we have proven the inequality that for any natural number n, the expression 2 minus 1 over n, all raised to the power of n, is greater than or equal to n. This completes our proof. All raised to the power of n is greater than or equal to n. This completes our proof. Welcome to this video where we'll be solving a mathematical inequality proof step by step using the principle of induction. Let's start with our example. We need to prove the following inequality. The sum of a 1 plus a 2 plus dot plus a n minus the product a 1 times a 2 times dot times a n is less than n plus 1. Given that 0 is less than a sub I, which is less than 1, and n is greater than 1. First, we'll verify the correctness of the following inequality. The product of 1 minus b sub I from I equals 1 to n is greater than 1 minus the sum of b sub I from I equals 1 to n, where 0 is less than b sub I, which is less than 1. We will prove the supporting inequality by induction. First, let's verify that the inequality holds for the base case, n equals 2. Now, let's establish the inductive step. We assume that the inequality holds for n equals k. Let's call this our induction hypothesis. We now need to prove that the inequality holds for n equals k plus 1. This is the induction step. Let's expand the product for k plus 1 terms. The product from I equals 1 to k plus 1 of 1 minus b sub I equals the product from I equals 1 to k of 1 minus b sub I multiplied by 1 minus b sub k plus 1. Now, we apply our induction hypothesis. We know that the product from I equals 1 to k of 1 minus b sub I is greater than 1 minus the sum from I equals 1 to k of b sub I. Let's expand this expression. We have 1 minus the sum from I equals 1 to k of b sub I multiplied by 1 minus b sub k plus 1. When we expand, we get 1 minus the sum from I equals 1 to k of b sub I minus b sub k plus 1 plus b sub k plus 1 times the sum from I equals 1 to k of b sub I. We can simplify this further to 1 minus the sum from I equals 1 to k plus 1 of b sub I plus b sub k plus 1 times the sum from I equals 1 to k of b sub I. Since b sub k plus 1 times the sum from I equals 1 to k of b sub I is positive, because each b sub I is between 0 and 1, we can conclude that this expression is greater than 1 minus the sum from I equals 1 to k plus 1 of b sub I. This completes our induction proof of the supporting inequality. Now, let's use this proven inequality to solve our original problem. If we let 1 minus b sub I equals a sub I, then b sub I equals 1 minus a sub I. Let's substitute this into our supporting inequality. Substituting into our inequality, we get the product from I equals 1 to n of a sub I is greater than 1 minus the sum from I equals 1 to n of 1 minus a sub I. Let's simplify the right side. 1 minus the sum from I equals 1 to n of 1 minus a sub I equals 1 minus n plus the sum from I equals 1 to n of a sub I. So our inequality becomes the product from I equals 1 to n of a sub I is greater than 1 minus n plus the sum from I equals 1 to n of a sub I. Rearranging, we get the sum from I equals 1 to n of a sub I minus the product from I equals 1 to n of a sub I is less than n minus 1 plus 1, which is n. But we need to prove that the sum minus the product is less than n plus 1. Since n is less than n plus 1, and the sum minus the product is less than n, we've proven that the sum minus the product is less than n plus 1. This completes our proof of the original inequality. Welcome to this math tutorial. Today, we'll solve a challenging inequality step by step. Let's look at our problem. Here's our example. We need to prove the following inequality: x cubed plus x divided by x minus 1 is greater than or equal to 2 times the quantity 2 plus square root of 3, where x is greater than 1. Let's begin. First, we'll rewrite our inequality by keeping the fraction on the left side and moving everything else to the right side. Next, we'll expand the right-hand side of our original inequality. 2 times the quantity 2 plus square root of 3 equals 4 plus 2 times square root of 3. For our third step, we need to find a common denominator for our expression. We'll multiply both the numerator and denominator of the expression on the right by x minus 1. Now, let's expand the product in the numerator. We have x cubed plus x minus the product of x minus 1 and 4 plus 2 square root of 3. Let's continue by simplifying the numerator. We'll combine like terms to make our expression more manageable. Let's further simplify by combining like terms in the numerator. We have x cubed minus 4x plus x, which gives us x cubed minus 3x. Then we have minus 2 square root of 3 times x plus 2 square root of 3. This gives us minus 2 square root of 3 times x plus 2 square root of 3. And we also have plus 4. Let's rearrange our numerator to group like terms more clearly. We'll write it as x cubed minus 3x minus 2 square root of 3 times x plus 4 plus 2 square root of 3. Now, for our final step, we need to analyze the inequality. Since x is greater than 1, we know that x minus 1 is positive. This means that the sign of our fraction is determined entirely by the sign of the numerator. Since x is greater than 1, the x cubed term will dominate as x increases, making the numerator positive for sufficiently large values of x. Therefore, the inequality is valid for all x greater than 1. Since x is greater than 1, both the numerator and denominator of the original fraction are positive. This means the original inequality holds true for all x greater than 1. Let's summarize what we've learned. In this problem, we started with a rational inequality and used algebraic manipulation to rewrite it in the form where we could analyze the sign of the fraction. The key steps were: first, rewriting the inequality by moving all terms to one side. Second, finding a common denominator. Third, expanding and simplifying the numerator. Finally, analyzing the sign of the fraction based on the domain x greater than 1. This approach can be applied to many rational inequalities. Remember to always consider the domain restrictions carefully. Thank you for watching this tutorial. Practice similar problems to strengthen your understanding of rational inequalities. Welcome to this math video, where we will prove an inequality involving powers. Let's start by looking at the inequality we need to prove. Our example inequality is a to the m plus b to the m to the power n is greater than a to the n plus b to the n to the power m, where n is greater than m. Let's follow the steps shown in the solution algorithm. First, we note that the expression is symmetric in a and b. This means we can assume without loss of generality that it is greater than or equal to b. Based on our assumption, we can define x as the ratio of b over a. Since it is greater than or equal to b, we know that x is between 0 and 1. Now comes a key insight. If we have n greater than m and x between 0 and 1, then x to the power n is less than x to the power m. From x to the n less than x to the m, we can add 1 to both sides to get 1 plus x to the n is less than 1 plus x to the m. Now we can take both sides and raise them to the respective powers. We raise the left side to the power m and the right side to the power n. This gives us 1 plus x to the n to the power m is less than 1 plus x to the m to the power n. Next, we substitute back the original value of x, which is b divided by a. Through algebraic manipulation, we can simplify this expression further. Let's continue with our algebraic manipulations to approach the final form. By multiplying both sides by a to the n times m, we get our original inequality. A to the n plus b to the n to the power m is less than a to the m plus b to the m to the power n. And that completes our proof. Welcome to our math tutorial. Today we're going to solve and prove an important inequality using algebraic manipulations and the Cauchy-Schwarz inequality. Let's start with the inequality we need to prove. We want to prove that the square root of the sum of quantities a minus b squared plus c minus d squared is less than or equal to the square root of a squared plus c squared plus the square root of b squared plus d squared, where a, b, c, and d are real numbers. First, let's understand our approach to solve this problem. Since both sides of the inequality are positive, we can square both sides. This is a valid operation because squaring preserves the inequality when both sides are non-negative. Let's square both sides of the inequality. We get that a minus b squared plus c minus d squared is less than or equal to the square of the sum of the two square roots on the right-hand side. Now, let's expand the expressions. On the left side, we have a squared minus 2ab plus b squared plus c squared minus 2cd plus d squared. On the right side, we need to expand the square of the sum. Remember the formula. The square of a sum equals the sum of the squares plus twice the product. So we get a squared plus c squared plus b squared plus d squared plus twice the product of the square roots. Now, let's simplify both sides. On the left side, we combine like terms to get a squared plus b squared plus c squared plus d squared minus 2ab minus 2cd. On the right side, we have a squared plus c squared plus b squared plus d squared plus twice the square root of the product. Simplifying further, the a squared, b squared, c squared, and d squared terms appear on both sides and cancel out. We're left with negative 2ab minus 2cd on the left and twice the square root of the product on the right. Let's divide both sides by 2. We get negative ab minus cd is less than or equal to the square root of the product. Now we need to analyze two separate cases. Case 1, when ab plus cd is greater than or equal to 0. Case 2, when ab plus cd is less than 0. Let's analyze case 2 more carefully. When ab plus cd is negative, the left side of our inequality becomes positive. So we need to prove that ab plus cd squared is less than or equal to the product term. Let's expand the expressions. On the left side, we have a squared b squared plus 2a bcd plus c squared d squared. On the right side, we have a squared b squared plus a squared d squared plus c squared b squared plus c squared d squared. Rearranging, we need to show that a squared d squared minus 2a bcd plus c squared b squared is greater than or equal to 0. This can be rewritten as a squared d squared minus 2a bcd plus c squared b squared, which equals a d minus cb squared. Since any squared real number is always greater than or equal to 0, we've proven that the inequality holds in case 2 as well. Therefore, the original inequality is always true for all real numbers a, b, c, and d. Welcome to our mathematical proof video. Today we're going to prove an inequality step by step following a clear algorithm. Let's start with our example. We need to prove the following inequality. The fraction a to the m minus b to the m over a to the m plus b to the m is greater than the fraction a to the n minus b to the n over a to the n plus b to the n. Given that m is greater than n is greater than b, and both a and b are positive, let's begin our proof. The first step is to make an observation based on our conditions. Since 0 is less than b, which is less than a, we can derive that 0 is less than the fraction b over a, which is less than 1. And since m is greater than n, when we raise the fraction b over a to these powers, we get that the fraction b over a to the power of m is less than the fraction b over a to the power of n. In our second step, we'll make some algebraic transformations. First, we note that the negative of b over a to the power of m is greater than the negative of b over a to the power of n. This implies that 1 minus b over a to the power of m is greater than 1 minus b over a to the power of n. Continuing with our transformations, we can also say that 1 plus b over a to the power of m is less than 1 plus b over a to the power of n. For our third step, we'll relate these transformed inequalities to our original fractions. First, we note that 1 minus b over a to the power of m greater than 1 minus b over a to the power of n implies that the fraction a to the m minus b to the m over a to the m is greater than the fraction a to the n minus b to the n over a to the n. Similarly, 1 plus b over a to the power of n greater than 1 plus b over a to the power of m implies that the fraction a to the n plus b to the n over a to the n is greater than the fraction a to the m plus b to the m over a to the m. In our fourth step, we'll multiply the two inequalities we've derived. We multiply the fractions and get that the product of a to the m minus b to the m over a to the m and a to the n plus b to the n over a to the n is greater than the product of a to the n minus b to the n over a to the n and a to the m plus b to the m over a to the m. For our fifth step, we'll simplify the products we just formed. After multiplying the fractions and simplifying the denominators, we get that the product of a to the m minus b to the m and a to the n plus b to the n over a to the m times a to the n is greater than the product of a to the n minus b to the n and a to the m plus b to the m over a to the n times a to the m. Since the denominators are the same, we can simplify to say that the product of a to the m minus b to the m and a to the n plus b to the n is greater than the product of a to the n minus b to the n and a to the m plus b to the m. For our final step, we'll rearrange to get our original inequality. From our last inequality, we can algebraically rearrange to get that the fraction a to the m minus b to the m over a to the m plus b to the m is greater than the fraction a to the n minus b to the n over a to the n plus b to the n, which is what we wanted to prove. Welcome to this math video where we'll prove an inequality using algebraic techniques. Let's start by looking at the inequality we need to prove. Here's our example. We need to prove that a squared plus b squared plus c squared plus d squared plus e squared is greater than or equal to a times the quantity b plus c plus d plus e, where a, b, c, d, and e are real numbers. Let's start our proof. The first step is to distribute the term on the right side of the inequality. We'll use the distributive property, which states that a times the sum of multiple terms equals the sum of a times each term. So, a times the quantity b plus c plus d plus e becomes ab plus ac plus ad plus ae. For the second step, we'll move all the terms to the left side of the inequality. We use the property that we can subtract the same quantity from both sides of an inequality without changing the direction of the inequality. So, we'll subtract ab, ac, ad, and ae from both sides. This gives us a squared plus b squared plus c squared plus d squared plus e squared minus b minus ac minus ad minus ae is greater than or equal to 0. Now, comes the clever part. We'll rewrite the left side by grouping terms using the method of completing the square. The general formula for completing the square is a squared minus 2ab plus b squared equals the square of the difference of a and b. To use this, we'll first break down our expression. We can write it as a squared over 4 minus ab plus b squared, plus a squared over 4 minus ac plus c squared, plus a squared over 4 minus ad plus d squared, plus a squared over 4 minus ae plus e squared. Notice that we've split a squared into 4 equal parts, with a squared over 4 going to each group. Let's now apply the completing the square formula to each group. For the first group, a squared over 4 minus ab plus b squared, we need to rewrite it in the form of a squared minus 2ab plus b squared, which equals the square of a minus b. To make this work, we need to adjust our expression. For each group, the middle term should be negative 2 times the product of the square roots of the first and third terms. In our case, the first term is a squared over 4, so its square root is over 2. The third term is b squared, so its square root is b. For the first group to match the completing the square formula, the middle term should be negative 2 times over 2 times b, which is negative ab. This matches our middle term exactly, so we can directly write this as the square of over 2 minus b. We can do the same for all the other groups, leading to the sum of 4 perfect squares. Now that we've expressed our left side as the sum of perfect squares, we can complete our proof. We know that the square of any real number is always greater than or equal to 0. Since our expression is the sum of 4 squared terms, and each squared term is greater than or equal to 0, the entire sum must also be greater than or equal to 0. This completes our proof. We've shown that a squared plus b squared plus c squared plus d squared plus e squared minus a times the quantity b plus c plus d plus e is always greater than or equal to 0. Rearranging, this means that a squared plus b squared plus c squared plus d squared plus e squared is always greater than or equal to a times the quantity b plus c plus d plus e, which is what we wanted to prove. Let's summarize what we've learned in this proof. First, we distributed the term on the right side of the inequality. Then, we moved all terms to the left side of the inequality. Next, we grouped terms using the method of completing the square, splitting a squared into 4 equal parts. We then applied the completing the square formula to rewrite our expression as the sum of 4 perfect squares. Finally, since the square of any real number is always non-negative, we concluded that the sum of these squares is also non-negative, which proved our original inequality. This technique of completing the square is very powerful for proving inequalities and is commonly used in mathematical competitions and advanced algebra. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.